So here it is. Let's look together. I just wonder if you have enough time, and it will be not desired to postpone, but look at it right now and develop a plan. Everyone knows how to do number one, right? Anyone has problems with number two?
That's just like the density matrix, right?
It's taking matrix elements of multiplying the taking integral similar to extra credit in previous homework, like sine x times sine x, sine x times x times sine 2x. So it's more mathematical challenge, but if you did it in homework previously, so it's more mathematical challenge. Number 3. So once we were computing the expectation value and propagation of wave function for superpositional state, and before the one that we did together was the same as here, only without this imaginary unit. So you scroll back to your previous calculations or to your previous memories and try to replace coefficient 1 over square root of 2 onto I divided by square root of 2. What about this one? It is Heisenberg equation of motion for expectation values, right? And the choice here is really most simple, trivial, similar to what was in class. The rest, 5 and 6, are again about this Heisenberg equation of motion in a little more complicated case when potential is not equal 0. So really we make it linear, and what we make it depending on current position. So it's different notations, but it is same as Heisenberg equation of motion. Let me interview you if, please lift hands if this set of equations bothers you. Okay, so no one else here, or everyone has an idea how to put it? I already got the idea. You don't need to hold it for. Please remind me who's taking differential equations. 1, 2, 3, 4, 5, 6. And you never tried the system of linear differential equations? What are you doing there?
I'm in it right now. So.
But what is in the class right now?
We just learned how to do second order differential equations.
Okay, good. Linear or non-linear?
Linear.
Okay, so then if you plug in, if you take second derivative of this equation, then on the right side you will have derivative of function y. And derivative is defined here. And then you will get the second order linear equation. Okay? So Kevin knows what to do. Give me a secret sign if you still have problems with this equation. Okay. Send me emails as you try to do it. Do not leave it for last night, so that we do collaborative. Again, there is no goal to torture young minds. There is a goal that everyone completes things in successfully in time. Yes, I by now I know how to freeze the class. One needs to ask about your memories, about the memories about previous material. So here's a little navigation map about what are we doing in the class. So we are pumping muscles, mathematical muscles, to go to more complicated and more realistic problems. Right now we do something really simple, but we are getting several tools. So we already covered the time independent Schrödinger equation, time dependent Schrödinger equation, Heisenberg for the space. And for particle in the box, we got density matrix and density of states, right? Remember this. Well. So very, very soon we will start new application, which will be a little bit closer to real life. And today we are on between the box and new chapter of oscillation. So there is a little gap between academic quantum theory just for passing exams and doing homeworks and quantum theory that people are using for practical life. So in and I'm trying to cover this gap a little bit. So this little tricks, little methods that we are covering, it is like different weapons in computer games against different monsters. It is what in fact is going on in practical quantum theory for real life, for professional activity. And what do you think when you hear the word basis?
What?
Basis.
Like what something is based off of?
Okay. But when after you are exposed to this class and maybe some math classes. Yes?
Like having to do with like logarithms and exponentials and stuff?
This is base. So natural base, but basis. It is not a new concept. We all were exposed here in this class. But try to. I know I'm getting an impression it's most unpleasant and torturing activity to browse through your own memories. Especially if it is not pleasant memories of visiting like of a party or visiting a beach or some sightseeing, but let's browse our memories about this class. So, did you ever heard the word basis in this class? If you didn't, it's my fault. Anyone heard the word basis in some math classes? Okay, my last hope is Ben. Did you ever heard the word basis in your research activity?
Not that I can.
Oh, you discouraged me so much.
Is it like the foundation that everything's built off of?
Philosophically, yes. But there is a much more specific, practical, and rigorously defined concept of basis.
Are you referring to basis set?
Yes.
Okay.
So what do you think about basis set?
Well, I like them.
Huh?
I like them. So.
But can you define for the rest of the class?
it's like a specific way of calculating. It's a specific way of calculating electron density.
Okay. And can you tell more? Do you use the same basis set, or you select them?
Well, most of the time you choose them based off the atom that you want to calculate density for.
Okay, okay, that's good. I do not think it helps us too much, but you've got general idea that there are some people who use the word basis in practical sense to represent something. Who is not aware of Taylor expansion? Not aware.
Oh, sorry.
Okay, now who is aware of Taylor expansion? Yes. Okay, so what? Thank you. So what is Taylor expansion?
Isn't it a way to add up the exponential of something using 1 over things? I don't.
So you are telling about representing exponential function as summation of several polynomial functions, like x to the power 0, 1, 2, 3. Right?
All over like the x, whatever power x is 2 to the factorial, right? It's
Yeah. Good. Is Taylor expansion a unique thing for exponential function?
It's something I'm guessing now.
No. So any more general definitions of Taylor expansion? Approximately. We are not here for any exams. It's just for cheering up the atmosphere. So huh? Where m
might actually be where.
so one can use letter m. So let's go with example that Alex did brought up. Exponential as a summation of several polynomial functions. So the idea is that one can represent any function, not only the exponential, as a summation of polynomial functions with specific coefficients. Okay? So a way to represent arbitrary functions through set of well-known functions. It's a great success. I wanted to write it down. X less arbitrary function is summation of known functions with some coefficients. So what? How it's called that e to the power x to the power x is equal to summation of 1 plus x plus x squared 2 plus x cubed over 3 squared, which is 6. And continuing the summation, right? Nothing new. And generally, one can tell that it is function 1 x to the power 0 plus x to the power 1 plus x to the power 2 plus so forth with coefficient c1, c2, and so forth. So this is idea of This is almost the idea of Taylor expansion, but there is a one more little detail that C sub m equals derivative of our arbitrary function of order n dxn, and there is a coefficient point one, yeah, derivative. But our main idea is that arbitrary function can be represented through a set of known functions. We do not need Taylor expansion in all details. We need this more general idea of representing one function through summation of others. We were already practicing it when we were doing an analog of the today next homework, when you were practicing superposition of ground and excited. So the state, non-stationary state of your particle in the box was as adding together known functions, sine of x and sine of 2x, basis functions which are known, right? Good. So I'm going to rewrite previous thing. X equals C naught. And instead of, before for Taylor expansion, we had polynomial function x to the power naught, we will put some general function. X C times 1. So if you are exposed to math classes, I should make a bet that it was either already presented to you or will be presented soon. So that if you the way of representing unknown functions through set of known functions is possible if the unknown functions form what? The word we started our discussion.
Basis set?
Yes. And it's better just to say complete. So if you take many functions that take arbitrary shapes, for example, we can take all functions that do exist in the universe. Definitely that if you design a new function, it will coincide with either one of already existing or as a summation of several or subtraction of already existing, right? The way is just how to select correct basis set. Okay? Any questions about this concept? Let's browse in our memories a little bit more. Were there any homeworks where we did practice the basis set? So there was one with superposition of ground and excited. What else? I don't remember all homeworks and all assignments, but I remember at least a few more. What about Fourier transform? You are representing some crazy arbitrary function like step as a summation of sines and cosines, right? Which are known. So in the problem about Fourier transform, your basis set was all trigonometric functions, sines and cosines with discrete set of let's say wave vectors. Good. Any other basis sets that you were exposed to? There is one more really important thing that you did successfully, and if you make an effort and scroll through the numbers, you will find it. What did we do to Gaussian wave packet, Gaussian shape? You cannot really just enjoy it, or you ignored it. But there was an assignment to find expansion coefficients of Gaussian wave packet over plane waves. Does it look something? Kind of. So we converted it from position space to momentum space, and we found this C sub k expansion coefficients. Remember? No? So it was another implementation of the same general idea. So these were your expansion coefficients, and your functions were e to the power minus I kx with different k, right? So exponentials with different wave vectors can serve as basis set. Trigonometric functions with different wave vectors can serve as basis set. Okay. Try to, if you didn't, if you haven't done, try to make your own definition of basis set and write it down. Michael, how do you define it?
So he uses these functions to approximate
What?
the electron.
Well, electron density is narrow sense for this, but generally any function. Yes. Okay.
It's a express arbitrary function and summation and non-function and coefficients.
Okay.
See
Good.
that.
Good. Anyone objects and wants some better verbalization? Okay. That's good for you. So I don't know how successful we will be today in reaching the end slide of the class, but this is the end slide. So all efforts will be to reach this equation. And just in case, as a backup, I probably just declare what it is, and then we'll try to go through things in an expedite mode. But I'm really happy that you are well familiar with concept of basis set. This is really good. So today's lecture is not practical, it is abstract. So we will assume that you know what is basis set, okay? And we will assume that generally for some problem we already know basis set. Then instead of doing all operations with wave function, instead of predicting future for wave function, finding observables, expectation values of some observable from experiment based on the wave function, which is like continuous distribution in space, we will work only with expansion coefficients of wave function in the known basis set. So if I'm telling some new ideas, you better record it. Okay. So we are converting from continuous wave function to discrete basis to discrete set of expansion coefficients, assuming that basis set is known. So instead of solving Schrödinger equation for continuously distributed wave function. We will solve Schrödinger equation for discrete set of expansion coefficients, which could be time dependent. As you already saw in our problem for superposition of ground and excited, 50-50%, and seeing that something happens. We saw that expansion coefficients became time dependent, and we found some interesting observables, right? So this is expansion coefficients, and those are matrix elements of Hamiltonian. So Hamiltonian, instead of operators as derivatives, partial derivatives, can be converted into a matrix. So wave function is converted into a vector of expansion coefficients, and any operator is converted into a matrix. So the goal, if time allows, is to go through details of this conversion. So in homework, well, assuming that we have basis set, like for particle in the box, it is just set of this sine functions, normalized sine functions. And in the homework where we looked at the superposition of grounded and excited, we assumed that first and second coefficients were 1/2, and the rest were zeros. We were skipping them. Some of you may already project the train of thought and tell there is nothing interesting. If we know eigenstates, if we select eigenstates as our basis, then any problem is already solved. What is the challenge? Who needs it? Rather than for poor and boring academic studies. You may ask this. And if you don't ask, I don't care, but if you do, I do have an answer. So remember when we were doing navigation map for the course, there were how many axes? We used 2, but there were 3, right? One axis is different methods, another axis is different systems, and the third is external perturbation. So something that is not explicitly taken into account. For most typical external perturbation is when, for example, you shine laser light on your molecule, or if you just put it on a stove and start to heat it up, or if you like just hit it with a hammer. So something that not explicitly included into Hamiltonian. So we can always play with Hamiltonian that gives us eigenstates and assume there is a little delta H, little addition to Hamiltonian because external world acts on our model. And then there will be really practically interesting things. So we are forming foundations to describe anything, to predict future not only of the poor box, but anything. And you already prompted me several times that our goal is to predict future. But we do have models that give answer of an observer. But the more general scientific approach is that there is also wet chemistry characterization lab experiment, and we are trying to design model based on what we know from experiment. And as soon as we predict outcome of the calculation, we set up a feedback loop and compare it to what is observed in the experiment, and we either interpret what is already available or we predict outcomes of experiments that haven't been done yet. Theory can predict and guide experiment in brave plans and in humble plans just to help to understand what has been measured. Good. Bra and cat notations. Give me a little sign if they're new for you. Okay, so you remember from, I know, the word remember is most scary word. But I hope that you remember from your presentations about MATLAB skills that there are row vectors and column vectors. Maybe you knew it from the chapter. So if we have a regular wave function, it corresponds to column vector. If you have conjugated wave function, it corresponds to the row vector, right? And most typical procedure of normalization when you have wave function with star multiplied by wave function integrated, it should be 1. So this convolution of two functions does have an analog in this space of expansion coefficients. In the space of expansion coefficients, it will correspond to row vector of expansion coefficients multiplied by column vector. I'm skipping derivation, hoping that you will trust. But if you trust this expression, then you practice row by column rule, and you will get the analog of normalization condition as C1 star C1, C2 star C2 plus so forth equals 1. So summation together of the squares of the expansion coefficient should give 1. This is normalization condition in the discrete space of expansion coefficients. If you have just one continuous wave function, it is integration. If it is in discrete, it's just row by column vectors. Next, there are a couple of ugly handwritten slides, but later on there will be nicely typed, if you have time to get to them. So, what is the main goal of quantum theory as part of physical chemistry?
Predict the future.
Predict the future in a little more practical sense, not future of everything, but predict the outcome of an experiment, like intensity of absorption spectrum at given wavelengths, or things like that. So this equation, which was I think postulate number 5, I don't remember who was presenting it. Maybe you do not know either. But postulate number 5 was that if you know a function and you know the operator corresponding to the stuff that you observe in experiment, then outcome, expected outcome, average outcome of the measurement can be formulated as wave function conjugated times operator times wave function not conjugated and integrate over the whole independent variable. So this equation was already postulated in postulates, right? And it was postulated in a form of continuously distributed wave function. But there is an analog of this most important equation in form of discrete expansion coefficients along specific bases. So if and just for simplicity, here are we assume we neglect higher basis states. We keep only the first and second. Otherwise, it will be too much writing. Although I have pre-made slides, it will be much reading. So our conjugated wave function. I'm too quick. Let me slow down and ask once again. What is bra and what is ket? I am too quick.
Is bra representing a row and ket representing a column?
Yes. Write it down. It's a standard notation. I'm scrolling one slide back, it should be empty. So row, as Alex told, is bra, angular bracket to the left, and column vector is cat, angular bracket to the right. And in 30 seconds, you memorize it forever. There will be a hint after which you will not be able to forget. Prepare. So when we are converting the protocol for finding an observable into language of expansion coefficients, first we just rewrite wave function conjugate, which will be basis function bra times expansion coefficients, basis function 2 bra times expansion coefficient, operator, then wave function cat number 1 with expansion coefficient, wave function cat number 2 with expansion coefficient. After we deform this, after we open brackets, you will see 4 terms like the following one. So product of expansion coefficients, C1, C2, times bra of wave function 1, operator, and then cat of the wave function 1. And more generally, there will be different indices. So the operator is taken into a bracket. Into a bracket of 2 wave functions, where left angle is bra and right bracket is cat. So 2 angular brackets. Bra cat is constructed of the word bracket. Okay? Bra. It is not different words. There is nothing with cat with whiskers. It's not C8.
It's the second sign that in the bracket, psi1.
Here, psi1, because I opened just the first term.
Okay.
Psi star bra phi 1 times A times C1 cat phi 1. But there should be 3 other terms. Yes?
What is the term on the left-hand side of the equation?
Term on the left side.
Okay.
Yes. It's angular bracket of A. So expectation value
Was that over time or not?
over time. Generally, everything is over time. Right. Right? You will not forget it. Okay. Same equation. Just type here. So we do have wave function bra, we have wave function cat, we have operator in between. And then we open brackets and obtain a pattern. Of 4 terms. Well, and if you have full basis, there will be longer number of terms. But they look all the same. So product of expansion coefficients to expansion coefficients, times bra operator cat. Product of expansion coefficients, they can be with different numbers. Bra operator cat. Product of expansion coefficients, bra operator cat. Product, bra operator cat. Okay? Now, I invite you to become directors of research institute, to plan scientific research rather than doing it yourself. Suppose that your subordinates will need to make millions of experiments with the same system. For example, with particle in the box of the given size. Initial conditions, like laser excitations, putting on a stove, microwave radiation, will be different again and again. But it will be the same box of the same size. And your subordinates will compute expectation values for different initial conditions with different expansion coefficients. So here is the question. Will this term bra operator cat change in each of these million experiments?
It's on the same system. No.
Yes. You hear what Alex said. You have a good potential to become director of a research institute. No. Which means that these coefficients, these constructions, bra operator cat, can be computed once and forever. Well, forever as long as we play with the same system, with the same molecule, with the same Hamiltonian, with the same basis set. So for each experiment, we will redesign initial conditions, and we will have different time propagations stored in this pair of expansion coefficients. But bra operator cat, the core element to compute expectation value, will be the same again and again. So if there are only 4 of them, we can compute them, tabulate them, and then use again and again to save a lot of efforts. In fact, your homework number 2 will follow this pattern. You will play with the same particle in the box. Initial conditions will be different, but all other things are the same. So you see that these objects can be labeled by operator and then the indices. If it is bra1 and cat1, it will be A11. If it is bra1 cat2, it will be A12. Bra2 cat1 will be A21. How do we call objects with 2 indices? Yes. And so this is most important element, not chemical element, mathematical element. Most important element to compute expectation value. And it behaves like a matrix. It's called matrix element. Matrix element of operator A. So this concept of basis set and concept of matrix elements, we can convert all of our processing quantum theory into matrix form, into form of vectors and matrices instead of continuous functions and differential operators. What is the goal? Why? Of course, when I was at the undergraduate times, I thought that the goal of quantum theory is Torchian minds, but it is not. Can you guess what what is the goal of converting from continuous functions into basis set? Is there any practical help? Yes?
It's easier for computers to compute.
Yes. Why?
They don't calculate 0 to infinity on every function. They only calculate what they need to.
Right. If you want on computers, if you want to represent infinite continuous function, you still need to discretize. But for fine discretization, you need like 1,000 to million points. Even if you have 1,000 points in each dimension and you have 3 dimensions, 1,000 to the power 3 will be already a huge number to keep an array in the memory. But if you already know basis functions, you deal, instead of like 1,000 by 1,000 by 1,000 array, you deal just with arrays of like 2 by 2 or like very brief arrays just for expansion coefficients, and you can do anything you like with them. Of course, for practical problems, sometimes it gets to hundreds, but still it is much, much smaller. What Ben was mentioning, he was mentioning basis set of atomic orbitals to represent electrons in molecules. And number of basis sets is approximate number of these petals, nodes, and loops for each atom, and then as many of those as many atoms. But it still will be a couple of hundred for true molecule. Okay. Good. We are over time. Let me just show what is missed. So we should finish here. We miss representing the same idea in basis of density networks. We don't have time now. And then the main thing will be to derive Schrödinger equation in the basis of this expansion coefficients to get the equation we started from. And starting point will be to plug in this expression of general function expressed as basis functions times expansion coefficients into time-dependent Schrödinger equation, use some of our philosophical discussions we had now, and arrive to the last equation, which I plan to show when we will meet next time. Meeting is dismissed. Here is my favorite slide. See you on Wednesday, and please send me emails about your optimism about completing homework in time. Wait a second. Would it, if you vote, well, I haven't decided yet, but if there would be chance to postpone homework by a couple of days. 1, 2, 3. Anyone against? H, you want you? Right. If there would be an opportunity to vote, how would you consider an opportunity to postpone the due date for homework?
Oh yeah.
Okay. Okay. Bye.
Yeah, tomorrow is
I don't work too. I work from 11 to 3 tomorrow.